This lecture is entitled Continuity versus Differentiability. This is a rather brief lesson compared to many. And as far as the hierarchy of you'll need to know everything that's in this lesson in order to be successful in calculus is probably debatable. But there's a reason why we would like to cover this, and it's covered in briefly in most textbooks. Let's start reading. So many theorems, and we could add or definitions start out as follows. Let f is a function, be continuous on a closed interval. Now, closed interval, the notation for closed interval is square brackets. And that means closed means it contains the endpoints. Let's give you an example. Suppose we're talking about the numbers on the number line from 1 to 7. Now, a closed interval from 1 to 7 would mean all numbers from 1 to 7, including the endpoints 1 and 7. And then we have over here and differentiable on the parentheses A to B. That's an open interval from A to B. That means all numbers from A to B, but not including the endpoints. Going back to our numbers from 1 to 7, the open interval from 1 to 7 would be all numbers from 1 to 7, but not including 1 and not including 7. It would mean it would include numbers like 1.1, 1.01, 1.001, and numbers like 6.9, 6.99, 6.999. Now, all intents and purposes, they're the same length, just by 1 point missing at the end. Okay, so to understand that, it's important to you read definitions over and over and over again, and theorems you will as you go through mathematics. And I don't know if you would be one to wonder, why are they adding this? Let me tell you one thing. We don't put excess verbiage into things, not in mathematics anyway. So if it's there, you can be sure that it's there for a purpose. So understanding why these terms are stated and how they have an impact is important. So let us begin. Continuity, continuous, okay, forms of the same word, means the graph of the function has no breaks. That means you can sketch the graph without lifting your pencil if the graph is continuous. Okay, if you have to lift your pencil to draw the graph, then it's discontinuous. Most of us are pretty okay with that as a way of describing it. Now, differentiable, first of all, the word differentiable comes from the word derivative, and the word derivative we have aligned with slope, have we not? So differentiable means that a unique tangent line can be drawn at every point on the graph. A unique, not just a tangent line, but one and only one tangent line at each point. The next line down, bullet point, a unique tangent line cannot be drawn at a sharp point. It says see figure 1. So let's come down here to figure 1 in front of us here. Okay. This is a V-shaped figure. You probably have seen the absolute value function, which is a V-shaped figure. This is a V-shape that usually goes V upward, this is downward. So maybe this is like negative absolute value function. At any rate, the sharp point right here, which is kind of covered up because of the lines, each of these lines, and I've only drawn 4, are tangent lines. They're of different color for emphasis. Okay, so there's not a unique one. There are a lot of lines that touch a sharp point only once. Now, some books don't talk about it in terms of a unique tangent line, and so that's something we're doing here that most textbooks don't. What most textbooks do is they show a V-shaped figure and they say the line that touches the graph at only one point, and that's a vertical line, has no slope. In other words, the slope is undefined. And they say since the slope is undefined, then it has no tangent line, and they go with it from that standpoint. I'm going to probably be addressing it more from this standpoint, but you're free to look at it, use that, especially if you're in a textbook that talks about it from that point of view. Reading on, figures 1 and 2 are different ways of explaining why it's not differentiable at a sharp point. And that's the thing we want to drive home. If you see a graph that has a sharp point, then it's not differentiable at that point, remember. Okay, not that it's not differentiable at other points, but at that point, it's not differentiable. And if a function is not differentiable at any point, then we say basically the function is not differentiable. The same can be said for not continuous. It's got to be continuous at every point to be continuous. It's got to be differentiable at every point to be differentiable. Okay, now let's look. A unique tangent line cannot be drawn at the endpoints of a graph. Here we have a graph, goes from here to here, and here's the endpoint. So we can draw any number of tangent lines to that endpoint. Okay. Now, that's basically why, when you go up here, why they've put this in. If any closed interval has an endpoint, any closed interval has an endpoint. It can be half closed. In other words, even if one end of it is closed and the other end is not. Okay. If one end of it's closed, it has an endpoint, which means it's not differentiable at that endpoint. Okay. So not only can you look at a graph and tell whether if it has a sharp point, it's not differentiable. If it has an endpoint, it's not differentiable. Okay, so we show that here in figure 3. A unique tangent line cannot be drawn at a single solitary point. Let's look at its figure 4 down here. Here's a point. How many lines can we draw through the point that have, touch it at only one place? And it's, again, we've drawn 3, and they're colored for emphasis. But so there you have it. So if you see a sharp point on a graph, it's not differentiable. If the graph has an endpoint, it's not differentiable. If the graph has a single point standing by itself, it's not differentiable. Now, a unique tangent line cannot be drawn where there's a break in the graph. Now, that means that if it has a break in the graph, it's not continuous. If the graph is not continuous, it's automatically not differentiable. If a graph is not continuous, it's not differentiable. Let's draw some conclusions here. A function is not differentiable at points where the graph is not continuous. That's what I just said. A function is not differentiable at points where the graph has a sharp point. Okay, that's what we just said. A function is not differentiable at a solitary point. That's what we just said. A function is not differentiable at the endpoints of a graph. Okay. So this is just repeating what we said up here, but it's worth repeating. Differentiable implies continuous. In other words, if a graph is differentiable, it cannot have any breaks in it. If it cannot have any breaks in it, it's got to be continuous. Got that? However, continuous does not mean differentiable. Let's look at the figure below. Here we have a graph. I don't know if it starts here, whether it goes off to infinity. This was lifted from another source, so that's not important. What's important here is the part of the graph you see here is continuous. In other words, I can draw this graph without lifting, in this case, my hand that the mouse is showing you, or a pencil. Does it have any sharp points? And yes, it does. It has 3 sharp points. So this is it's not differentiable. So this graph is continuous, but it's not differentiable. So if it's continuous, it doesn't have to be differentiable. But if it's differentiable, it has to be continuous. Let's come down here. So we're just restating some things here. If a function is differentiable, that means it's also continuous. That's important. Differentiable implies continuous. True. Okay. Continuous implies differentiable. That's false. If it's not differentiable, it's not continuous. Not true. We just saw one. It's not differentiable at the sharp points, but it was continuous, so that's false. Not continuous implies not differentiable. If it's not continuous, it's not differentiable. That is true. Explaining continuous or not continuous is easy. Look at these 2 drawing graphs we have here. It's very easy to see that this is not continuous because I have to lift my pencil here. I have to lift my pencil here. I have to lift my pencil here. Okay, so it's not continuous. How about differentiable? That's not so easy. This is not differentiable for 2 reasons. 1, a sharp point, and 1, a solitary point. This one's not differentiable because of a sharp point, okay, because of an endpoint, okay, and because this point is not in the domain. Now, anything, if something's not in the domain, it's not in play. It's not in play. Okay. So this is not differentiable for several reasons. One is it has points, it's not continuous there. And some people might say, let's just say it's not continuous. That is true, but why is it not continuous there? It's not in the domain. Okay. And likewise, now, if this point were not, this circle right here were not shaded in, then we would say that 0 is not in the domain. That would be the reason, because it wouldn't be a sharp point. See, this is not a sharp point here. Okay, because it's not an endpoint. In fact, this, I assume we could say this is stopping here, so there's no unique tangent line here. Okay, so there are a lot of reasons. That's why I say explaining differentiable or not differentiable is not so easy. Explaining continuity or not continuous is easy. Just before I leave these figures, I want to make one point. Why could I shade in this open circle here and make this continuous? And could I shade in this to make this an endpoint? Okay, and the answer is no. I cannot shade in this, and I cannot shade in this, not unless I make some adjustments. In other words, if this point stays, I cannot shade this in. Why? And you can't answer for me, but think to yourself, why can I not shade in here? Because it would not be a function, would it? In other words, that would mean at 1, I get this answer and this answer, 2 different answers for the same input value. That is not a function. We don't emphasize enough in mathematics why it always says if f is a function. If it's not a function, we really don't want to deal with it. I mean, it's really, think about it. If you worked a math problem and you worked it and got two different answers doing it, everything correctly, and kept getting different answers, and everybody was right with the different answers, that would seem a little absurd, wouldn't it, or dangerous. Same thing is true here. If I shaded this in. Now, that's not part of this lesson. This is just part of making you realize that things that you, when you're looking at a graph, remember, people make up these graphs. Many of them, myself, the narrator here, has made up the graphs. You have to be certain that you don't violate any of the rules of mathematics. Now, let's look at three graphs in closing. These graphs are all different, but they all have something going on at x equals 3. Now, at x equals 3, I have to lift my pencil. There's a hole there. At x equals 3, I have to lift my pencil. It jumps to another graph. At x equals 3, I stop here. I have to go up here and put a dot and then come back down. So none of these graphs are continuous. But now let's talk about differentiability. This graph is not differentiable at 0.34, okay, or when x is 3, because x equals 3 is not in the domain, okay. This graph is not differentiable at 3,4 because it's an endpoint. Now up here, this point right here, which would be 3,6, I believe, is not an endpoint. And of course, we couldn't have them both be endpoints for the same reason we talked about in the previous discussion. That is, it wouldn't be a function. This one, you know, if we didn't have this dot up here, this and this, these two would be the same. We have a point up here. And so we have a point here. And so this is not differentiable at that particular point, 3,7, because it's a solitary point. Okay. So definitions read continuous and or differential because breaks in a graph and sharp points in a graph present problems. And so it's put there in the definition to make you know that there are no problems with this particular graph. That's why when we go back up to the beginning, that beginning statement they're put in to allay fears to the reader of the problem or constraints that are going to take away problems that would exist otherwise. So this will be the conclusion of this lesson.